So either during class or immediately after class, I realized that I didn't go through the full 4-step hypothesis testing procedure for a correlation. And the step 1 and 2 are slightly different than other statistical tests, and so it needs to be done. So what I'm going to do is, for this sample exam question, I'm going to go through the full 4-step hypothesis testing procedure so that you have that as a demonstration. And I'm doing it in front of a whiteboard on Zoom so that it's as similar to lecture as possible, although it's not live. So this question asks, compute the Pearson correlation for the following data using the full 4-step hypothesis testing process. Use a two-tailed test and an alpha of 0.01. So on this question, the first part is that we need our hypothesis. And the hypothesis, it's a two-tailed test, and we need that piece. Two-tailed. We are going to have, so for step 1, we're going to have, just like before, we're going to have our null, and we're going to have an alternative. And for a two-tailed test, and afterwards I'll go over what these would be for a one-tailed test, but first I'll do the full video for this example. For a two-tailed test, the symbol for correlation is rho, spelled R-H-O, rho. And the correlation is, or the hypotheses is, that rho is equal to 0. Rho is not equal to 0 because it's a two-tailed test. We have the equals and does not equal. And the question that we're always asking with the correlation is whether or not the correlation is different than 0 in this case, or if we have a one-tailed test, whether it's bigger or smaller in a particular direction. But for this example, we have a two-tailed test, so null is rho is equal to 0. Alternate is that rho is not equal to 0. For step 2 of the hypothesis testing procedure, we need our alpha level, which I'm going to flip back to the other screen. I believe it was 0.01, but I want to double check that. And sure enough, it is. Alpha is 0.01. We have a two-tailed test. We also need to calculate our degrees of freedom, which is n minus 2. And our n here was 7. Okay, so we have to calculate that value. So I'm going to stop my share for a moment. So we need that it's a two-tailed test. We need our alpha. We need our degrees of freedom, which is 5. And what we're going to do is then we're going to go to table B6 and find that critical value. So I'm going to table B6, critical values for the Pearson correlation. And I've got 5 degrees of freedom. So I'll line that up at the bottom there, right? 5 degrees of freedom. And I have a two-tailed test with an alpha of 0.01. So level of significance for a two-tailed test, 0.01. And I'm going to go down, and the significance value is the critical value, the critical value is going to be plus or minus, because it's a two-tailed test, 0.874. What that means is if the number that we calculate is more extreme than 0.874, either bigger or smaller, right? Then we're going to reject the null hypothesis and accept the alternate. So if we look at that, drawing it out, okay, we've got negative 0.874, positive 0.874. These two cutoff values here. Okay. Anything in here, fail to reject. Null. Anything that's out in the tails, that's where we're going to reject the null and accept the alternate. Now what we need to do is calculate the test statistic. We need to calculate R. In order to calculate R, we have to calculate the sum of products, sum of squares X, and sum of squares Y. So I'm going to share my screen so that you can see those values. So I'm going to copy out all of these values for myself, because that way I won't have to keep flipping back and forth to the screen. And I recommend that you do that for yourself too. Having all of those numbers in one spot is helpful. So I've got sum of X. It is 34. The sum of X squared, which is take each X, square it, and then add it up, is 218. The sum of Y is 93. The sum of Y squared is 1,285. The sum of XY is 422. And N is 7. With these values, what I can do is I can calculate my sum of products, my sum of squares X, and my sum of squares Y. And I'm actually going to erase this because I'm going to need this space, and then I'll just have to draw it later. Just how it goes. Okay. So SP. The formula I'm going to use is the computational formula. That is sum of X, Y, subtract the sum of X, multiplied by the sum of Y, divided by N. The sum of XY is right here, 422. The sum of X is 34. The sum of Y is 93. Divided by 7, because that's the sample size right here. So I have 422, subtract, find a calculator here. So I have 34 multiplied by 93, which is 3,162 divided by 7. 422, subtract 451.71. Which is negative 229.71. What that tells me is that when I do end up fully finishing and calculating R, that R is going to be negative, because the sum of squares of X is always positive. The sum of squares Y is always positive. So the denominator of the R calculation is always positive. That tells me that the numerator is what determines whether or not the correlation is positive or negative. This sum of products is negative, so the correlation is going to be negative when we get there. We're not there yet. Okay? Now what we need to do is we need to calculate sum of squares X and sum of squares Y. Sum of squares X is equal to the sum of X squared minus the sum of X, which is then squared and divided by N, Remember, this better be a positive number. Because what a sum of squares is it's the sum of the squared deviation scores. So if the deviation score is positive, then it stays positive. If the square of the deviation score is negative, a negative squared, sorry, of course this, and a negative value squared, it becomes positive. And sorry, this should be 7. So I have 218 subtract 34 squared, 1,156 divided by 7. Which is 165.14. It's 2.86. And I need to do the same. Should have written a bit smaller, but this is what it is. I need to do the same for the sum of squares of y. Okay, so the sum of squares y is the sum of y squared subtract the sum of y, which is then squared divided by n. Okay. So the sum of y squared was 1,285. Subtract sum of y was 93 squared divided by 7. 1,285 subtract 93 squared is, check that, something massive. It's 8,649 divided by 7 though. $1,235.57. Still got this one. There's a decimal right there. Which is 49.43. So what I'm going to do is I'm going to multiply 52.86 by 49.43. I'm going to take the square root of it, and that is my denominator for my r. So come back over here. And by virtue of having only one whiteboard, I'm going to have to erase some values. I'm going to erase this. We don't need this information anymore. And this is all step 3 of a hypothesis testing procedure for a correlation. Equals sum products for the square root, the sum of squares multiplied by the sum of squares of y. Sum products was negative 29.71. Then sum of squares x was 52.86. And the sum of squares of y was 49.43. So the way that looks is this. So if I take 49.43 and I multiply that by 52.86, in 2,612.87, whatever this number is, better be larger than 29.71. Because if it's smaller, then my correlation is bigger than, or more extreme than -1, and it can't. If we get that number, then we know that we've done something incorrect. Sure enough, that's -29.71 divided by 51.12. 29.71 divided by 51.12 is -0.58. This is the value. This is our end part of step 3. This is what we compare to the value in step 2, which I'm going to have to look up again because I erased it. And that's what we'll be comparing. So for step 4, what we're going to do, I'm actually going to pause this so I can just grab those numbers. Okay. So the value was plus or minus 0.874. The value we just calculated is -0.58. So in terms of decision and evidence and conclusion, that we have all of the parts that we need to full marks on the exam, we are going, it's in this middle spot, right? That's fail to reject the null. Your evidence can be this picture, right? And then interpret it. No significant relationship no significant relationship between X. And that's your full 4-step. That's the full 4-step hypothesis testing procedure for a correlation. All right. And so on that note, let me know if you have any questions before the exam. I am here to help and happy to help.